Alright, so today we're looking at our first topic is derivations of free algebras. Starts with a proposition. I'm going to let x be a set. M a Lx module and D a mapping from X into M. Exists a unique linear mapping D of Lx into M extending D such that D of the bracket of A and A prime is A on D of A prime minus A prime on D of A. We define or is that supposed to be part of the proof? I think so. It is not marked. Define a Lie algebra G with underlying module. I'll write it as on a module M times the Lie algebra, free Lie algebra of X by the bracket of module element times free Lie element times M prime being A prime. Our element in the module is the action of A on M prime minus the action of A prime on M, and our free Lie element is just the pre-existing bracket of A and A prime. Let F be the homomorphism of Lx into G such that f of x is equal to our mapping by D, giving us the element in M, and then just the image in the free algebra. This is for x in our generating set. Let f of A be D of A with U of A for all A in Lx. Then U is a homomorphism of Lx into itself. As U of x equals x for all x in X, U of A and A for all A in Lx. So f of A is D of A and A. And so we get our desired relation. Conversely, let let D prime be as desired, as a map from Lx into M with the desired relation extending D. Let f prime of A then be D prime of A and A for all A in Lx. So f prime is of Lx into G is a homomorphism with f on x. So f prime is f, and then thus D prime is D. Every mapping of x into Lx has a unique extension to a derivation of Lx. Proof: when M is Lx with the adjoint representation, D from above is a derivation. Elimination theorem. Proposition. Let S1 and S2 be disjoint sets. And D be a mapping of S1 times S2 into LS2. Let G be the quotient of the Lie algebra of the union of S1 and S2, the free Lie algebra of S1 and S2, by the ideal generated by the elements of the bracket of S1 and S2 minus the function D, S1 and S2. With S1 and S2 in their respective sets. Let C be from LS1, S2, the union of S1 and S2 onto G canonical. Then part A of our proposition. Phi I defined as the restriction of C to Si can be extended to an isomorphism of L of Si onto a subalgebra AI in G. Part B is that G is then A1 plus A2. The intersection of A1 and A2 is 0, and A2 is an ideal. of G. And the proof. So we're going to let Ci be the homomorphism of the Freely algebra of Si into G, extending Ci and Ai with image Ai. So Ci Si generates Ai. Okay, let's write D to be the adjoint of the image under phi1 of S1 for some S1 in S1. The derivation D of G maps elements of phi2S2 into A2 by the relation that the bracket of phi1 of S1, phi2 of S2 is going to be psi2 of D of S1 and S2. As A2, of course, is generated by phi2 of S2. So D of A2 lies within A2. The set of X and G such that their adjoint leaves A2 invariant is a Lie subalgebra of G containing phi1 of S1 by the above, and hence A1. Hence the bracket of A1 and A2 lies within A2. Thus A1 plus A2 is a Lie subalgebra of G. And A1 plus A2 equals G as it contains the generating set of phi1 S1 union phi2 S2. For all S1 and S1, there exists a derivation ds1 derivation of L S2 such that derivation ds1 of S2 is just d of S1 and S2. Then the mapping of our S1 into the derivation of S1 can be extended to a homomorphism D of ls1 into the derivations of L of S2. Let H be the semidirect product of the Freely algebra of S1 by the Freely algebra of S2 corresponding to D. As a module, it is then ls1 times ls2 with, in particular, the bracket of an element in S1 on its own with the element in S2 on its own is 0 and D of S1, S2. Thus exists function f of g into h, a homomorphism such that f of phi1 of s1 is s1 comma 0 and f of phi2 of s2 is 0 and s2, giving us the f of c1 of a1 plus c2 of a2 gives us a1 and a2. So c1 and c2 are injective. Yeah, let me call these a hat. I don't know why they're so insistent on using variables with the same names as sets and like not really delineating between them. And our sets a1 and a2 have trivial intersection, and so we are done. After that is a proposition. Let X be a set with a subset S and T the set of sequences of S1 through Sn X with each S I in S and X in X minus S. Part A of our proposition, that Lx is a module, is the direct sum of the subalgebra L of S and the ideal A generated by X minus S. Part B, there exists phi from LT into A, which is an isomorphism mapping S1 through Sn on X to the composition of the adjoints of each element in S to X. Now, proof. Let G be the Lie algebra from constructed about in the last one. With S1 equals S, S2 equals to T, and D of S and T being S through S1 through Sn X, for T being everything on the right. S and S1. And of course we're going to identify the free Lie algebra of S and T with their canonical images in G. Now, we're going to let C be the mapping of T into Lx of the same form as our feed from the proposition. Now, C of D of S and T is the bracket of S with C of T. Hence, there exists a homomorphism alpha from G to the free Lie algebra of X with alpha restricted to S being the identity of S, and alpha restricted to T being our C. Now we have the X minus S's in T with there then being a homomorphism beta of Lx into G with a restriction of X, restriction to X being the identity. Of X, of course. Alpha is an isomorphism with inverse beta. We gotta show that here. 1 second. As C of X as X for X in X minus S. We see that alpha composed with beta is on X is the identity. So this can be extended to our free Lie algebra. We also see that the bracket of S and T is our D of S and T in G by construction. So T as S1 through Sn and X is equal in G to the composition of the adjoints. X, so T is beta of alpha of T. So beta composed with alpha is identity on all of G. As alpha is an isomorphism, we see that the restriction of alpha to the free of T is an isomorphism phi from LT onto H, an ideal, of Lx such that Lx is the direct sum of Ls and H. So we have that phi of S1 through Sn of X is the composition of the adjoints. Hence, phi of T is an A. Where B is an A since phi T generates B as a subalgebra of Lx, but B is an ideal, and X minus S lies within phi of T lies within B. So alpha lies with A lies within B. This comes with a corollary. I'm going to let Y and X in the Freely algebra. Lx is the direct sum of the free submodule k dot y and the Lie what's happening subalgebra admitting as a basic family sorry, something weird's going on with my tablet thing. The family of the adjoints, adjoint of y composed n times on z for n being a natural number including 0 and z being x and nx and not equal to y. The proof of this is very straightforward. From the above, when Rs is just y. Now, okay, first off, this isn't quite long enough, I don't think, for a video, so I'm going to stall a little bit, but the next couple topics are on the p-Hall sets in a free magma, and they, go through the definition again. It's literally just the same thing as from before. I don't know if this is a mistake, but I think like I might just skip over all of this because it seems to be almost exactly case for case just what we saw before. And to be honest, I didn't really enjoy the discussion of Hall sets all that much. I didn't think it was super interesting or fun or whatever, so yeah, we're gonna call it here. I don't like that my videos are kind of getting shorter, but I don't know, I'm getting lazier. Like, I did kind of cover what I wanted to already in this series, but I do want to keep going through the rest of the books, so we will keep going in the future. I don't know what I'm saying.